Hello, Assalamualaikum warahmatullahi ta'ala wabarakatuh. We are not started yet. This is just a testing. Okay. Assalamualaikum warahmatullahi ta'ala wabarakatuh and salam sejahtera. So welcome to our online feedback control analysis discussion for our process control instrumentation class today. Ya Hafiz, Waalaikumsalam Hafiz. Okay, so how are you guys? Hopefully everything is okay under that this MC apa PKPB announcement for your test two tomorrow night. We'll have two questions for this test two, the second test. The first question will be covered block diagram, transfer function, and also dynamic behavior of the closed loop. Whereas the second question covers on stability and tuning. All right. So we're gonna discuss on this feedback control analysis. But before that, I would like you to answer the survey. Let me share the screen first. All right, guys, please go to menti.com and answer this survey about your understanding in feedback control analysis. I will use this input from the survey to for the points for our discussion. I'll give you another about 3 minutes more before we do the discussion on this feedback control analysis. I will show you the result now on this. What is it? On this feedback control survey. Yeah, we have feedback control diagram is the one that you most understand, the most understood. Okay, the most difficult is the tuning. Wow. All right. So the input is still coming. Surprisingly, that you are quite easy with the stability rather than dynamic behavior. Wow. Okay. So don't worry. We will start discussing on this input in about 5 minutes, or no, 3 minutes. Okay, in time, in 3 minutes. But by the way, you can uh, comment start commenting in the chat if you have a question that you want to ask, or you want me to make it clear for you. Okay, type the comment and I will try to answer it. By the way, guys, while uh, typing or commenting this YouTube live, so make sure that you try to subscribe it so that you can have some information. You can obtain some information about process control, about the teaching and learning in the latest trend in teaching and learning, and also how to be edutubers. Edutubers mean educational YouTube content. It's the one a person who contributed the content to educational content in the YouTube. So subscribe my channel in order for you to get more information about YouTuber, EduTuber, process control, and teaching and learning. All right, there are several questions basically already asked, but I'll try to answer it after this sharing information. All right, guys, let's take a look at this composition control system for a stirred tank blended process. Before this online session, some of your friends asked me about what is the difference between our uh, controls class with the electrical control class. All right, for your information, our control class is called process control and instrumentation, or process control system. Whereas for others, non-chemical engineering, they're just the class, or the course is called control system or control theory, whatever. So the difference is in our syllabus, we have process. That's why in the beginning, we start with the process. We identify the process. We identify either the process is continuous, either the process is batch or semi-batch, and we also identify either our process is a seesaw process, single input or single output, single input, single output, or MISO process or MIMO process. So that is different with others. And after we identify that process, then we do the modeling of the process, mathematical modeling of the process. Okay, and I'm not really sure whether non-chemical engineering also have a modeling in the process control syllabus. That's why our course, the process control course, is much tougher than others, because we need to do the modeling, and after that we convert it. We develop the mathematical model in the form of ordinary differential equation, ODE, and after that we do Laplace transform in order to change it from the for the time domain into the space domain. And after that, we develop a transfer function. Okay. I think the others will start with the transfer function, if I'm not mistaken. All right, so hopefully that's clear about the question how our controls class is different from other non-chemical engineering. All right, so let's take a look at this diagram of the blending, straight time blending process. This is not a CSTR because we don't have a reaction here. We have a composition control here where you want to monitor and control the composition of this blending system by manipulating the second flow rate of the input. We have a first input W1 and X1 as a disturbance. So this is a constant level, okay, constant level system, since we have the effluent basically discharged at a certain level, at a certain height. So no need for us to control the level here. All right. So from this, what's in our previous classes, once we are given this kind of simple process flow diagram with a certain instrumentation, we cannot call this pen idea because this is very simple. We start with the process control variable analysis using what we call it variable table analysis. Okay, we need to identify what is our control variables, what is our process variables, not process variables, sorry, measured variables, manipulated variables, and also disturbance. So once we identify all of these, then we do the modeling, mathematical modeling on the composition, for example, in this case, and also the mass balance. So we have a composition balance and we have a mass balance, and after that, we do the Laplace transform, and from this Laplace transform, we can obtain two different transfer function, which is GP, the process, which is a relationship between the composition with the W2, and the second one is disturbance transfer function. So it's a relationship between the X, the composition, the outlet composition, with either the flow rate of the first stream or the composition of the first stream. All right. That is basically what we have learned previously, or what basically has been asked, has been tested, or has been assessed in your test 1. Okay. Then we come up with this, what we call it closed loop transfer function, block diagram, or feedback control block diagram. One important thing that you need to do is you need to transform from this process diagram into a block diagram with all information related to all the transfer function and also the stream information. Remember, stream need to be labeled in terms of variables and also in terms of units. This is very important. For example, in your test 2 tomorrow, you will be asked to develop this block diagram for a given process flow diagram or for a given feedback control diagram. So make sure you label everything, label the stream together with the units, and if you're given a value of your transfer function, either the disturbance transfer function, the process transfer functions, the measurement transfer function, the valve, the controller, if you are given, please put that value in your transfer function. Okay, so that is very important. And the most important thing is make sure that the line, all right, the line, let me put my laser pointer over here. All right, this is very important. This line should not be come from this circle process here. Make sure it is from the output. You need to draw a line directly from your control variables, not from this additional circle here, right? From our exercise, yes, some of you basically you drag a line from here, so it should be from the control variables. Okay, that is very important. Okay, please take care of that. So that's why in your survey, the block diagram is, you don't have any problem in the block diagram. Okay, so share let me share the output from the survey. All right, so we have a feedback block diagram that is the most easier for you. And then after that, you have a transfer function followed by stability, dynamic behavior. I don't know why dynamic behavior has become very difficult for you. And lastly, the tuning. Right? Tuning, yes. I do admit that the tuning is the most difficult subtopic in this feedback control analysis. All right, so we have discussed the block diagram. Make sure that you label your block diagram together with the transfer function value, label correctly for all the stream together with the unit. Okay, and after that, once you have done draw your block diagram, then you need to develop the transfer function. Remember, for this transfer function, we have two problems: the servo problem and also the regulatory problem. Make sure you're able to develop a transfer function for these two problems if you are asked to derive. Okay. Otherwise, if you are asked to, for example, analyze the dynamic behavior either for the servo or regulator, make sure you choose the right transfer function for that. Make sure you know that for the transfer function, for the servo transfer function, okay, there shouldn't be any GD over there. Okay, and once you obtain the transfer function, then please make sure transfer all those value given for all those transfer functions, such that you can simplify that transfer function into a polynomial equation in terms of polynomial equation. Okay, in terms of polynomial equations. So I don't know, either it can be a first order system, it can be a second order, it can be a third order, higher order, or it can be yeah, if it's a higher order, then you need to transform it or estimate into first order plus time delay. Now we are talking about the dynamic behavior. Okay, we are talking about dynamic behavior for this block diagram. So you need to first draw the block diagram, put all this value, label all the stream, and after that you develop a transfer function. Or if the question asks you to develop, you need to derive it. Otherwise, you just pick either that this is for the servo or this is for the regulator, depending on the question asked of the question asked. And then after that, you replace or you transfer all the value for your transfer function into this block diagram, into this transfer function, and simplify that equation. Okay. Once you get the simplified transfer function value or equation in terms of polynomial, then or in terms of you need to have a numerator and also denominator, and after that you identify either it is belong to what kind of transfer function. What is it, the first order transfer function, Is it a second order transfer function or higher order transfer function? And from that, you need to sketch the response. Okay, since you are having a problem in a Simulink, usually we suppose we need to ask you to plot it using Simulink. But now, since you're having a problem, so we just ask you to sketch it. Make sure you know what should be your initial value by using initial value theorem, and make sure that you know what is your final value by using a final value theorem. And in between, you need to make sure you know that if it is first order, then what should be the response of the first order. So you know the initial value, you know the final value, and in between is depending on either first order, second order, or higher order. Okay. First order, I think is very easy. Okay, since you only have a one tau, one time constant. But the most important is you should able to differentiate between several type of under a second order under them. Right? You have three types of under them response: critically them, over them, and also under them. So which is depend on the damping coefficient. So make sure you're able to identify what kind of under them second order response that you have after you already put all those block diagram value. Okay, after you put all those the transfer function value for your instrument, for your process, for your disturbance whatsoever. And from that, you need to identify, okay, this is, for example, if the zeta is equal to 1, so what kind of under them response? Define the name, and after that, you sketch the response. Okay, over them and critically them is almost the same, but make sure you know. Okay, if it's under them, so make sure you know why that it is under them, and you know under them there will be some oscillation. So that's all that you need to do for if the question, or if you are asked to sketch the dynamic response of your closed loop transfer function or closed loop transfer function. Okay. All right. We are very clear with the feedback block diagram, and then the transfer function. Please choose the right transfer function either for the servo or regulator. And then after that, you will ask the dynamic behavior, sketch the dynamic behavior. Identify the response first, and after that, you sketch the dynamic behavior. All right. So that is for the feedback block diagram, transfer function, and also dynamic behavior. Next, we'll go for the stability. Again, using block your block transfer function, using this what we call it, wait, the block diagram is still depend on your block diagram and also the transfer function. Right. So basically, for the feedback control analysis, this block diagram is the most important diagram that you need to understand it. If you're not really clear on this block diagram, then you cannot do the transfer function. You cannot derive your transfer function. Okay, that is the first. You cannot derive your transfer function. If you don't understand this block diagram, you cannot also analyze the behavior of your closed loop system. Have a second. The third one, you cannot do your stability. It's very difficult for you if you cannot come up with the simplified transfer function equation. Okay, it's very difficult for you to do the stability because the stability requires you to have in terms of polynomials. Okay, in terms of polynomials. And the fourth or the last one, if you don't understand the block diagram, you cannot do the tuning also, because the tuning also depend on this block diagram. Right? So this is the most important concept in our feedback control system analysis. All right, the stability. The stability is quite simple. Once you already obtain this, or either given or you are asked to derive it, and after that, make sure that you convert it into a polynomial form. And after that, you will do the checking. The general criterion, you need to do the checking for the general criterion. All right, check all those coefficient, all the first coefficient, the highest coefficient should be positive. If it's negative, then you need to multiply all coefficient with the negative sign, and then check if there is any coefficient negative sign in all coefficient. If there is at least one coefficient is negative, therefore you'd stop because it's already unstable. If all the coefficients are positive, therefore you need to do the rod stability criterion. Okay, the rod array. Do the rod array. Okay, that is basically stability. Right, stability. Next, we will have tuning. Okay, stability, as I mentioned before in our online class, stability is just finding a range of your controller, either the P controller, the PI controller, or PID controller. You just identify the range of your tuning parameters. Whereas for your tuning, you need to identify or calculate one single value for all your tuning parameters. Okay, there are several methods that you can use to tune this controller. All right, but in this syllabus, we just use offline and online. Offline is using Cohen-Kuhn, whereas we use Ziegler-Nichols for the online tuning. All right, Cohen-Kuhn or offline tuning required you to have a PRC response, okay, which can be done offline. That's why we call it offline tuning. Okay, you close or you off the controller over here. Okay, you disable this controller and you step change your valve or your input to the valve and monitor your control variables. And from that process reaction curve response, then you estimate using 1-point method or 2-point method and come up with the first order plus time delay model. And from that, you can substitute all those parameters in the first order plus time delay model to the Cohen-Kuhn tuning equations direct. Okay, offline is very direct. If you're given the PRC, just estimate it and substitute into the Cohen-Kuhn equation. That's all direct. Whereas for the Ziegler-Nichols, for the online, you need to do a lot of things. First, you need to do the online tuning first. It's not tuning, it's basically online tuning, finding the online tuning parameter, where you need to change some of the tuning parameters to make sure that you obtain a constant oscillation response of your output or of your control variables. And from that, you will do the certain analysis, finding the ultimate period and also finding the KC, the ultimate KC, such that will give you that constant oscillation. And from that, you just substitute into a equation model. That's all. All right, so next, let's look at your questions. Hopefully there is several questions here. So guys, if you have another question, just comment it here such that I can able to answer it. All right, the first question from Izati Azrael. Delta, if we obtain value of Kc using Cohen-Kuhn equal to 2.7 and Ziegler-Nichols equal to 1.2, therefore offset from tuning method for Cc is lesser or less compared to Ziegler-Nichols, right? How can we justify it? All right. If you're having this kind of problem, so the most important thing that if you're using P controller, of course, P controller will always have a offset. How you select the best tuning method based on the degree or the value of your offset. So you need to calculate the offset. Okay. You cannot justify that it is because of the Kc value is bigger than Cohen-Kun Kc value is bigger than Ziegler-Nichols, therefore Cohen-Kun is better. Okay, you cannot justify something like that. You need to justify it based on the offset value. Of course, if you have a bigger Kc value, you will have a smaller offset. But in your answer, you need to justify based on offset, not based on the Kc value. Okay? Justify it in terms of offset, and from that, you can justify that, you can answer it that the Kc from the Cohen-Kun tuning is better because the offset is smaller than Ziegler-Nichols. But you need to calculate the offset first. All right, Izati? Okay, another question here. How does the poles and zero in transfer function determine the stability of system, and how to transfer it into a response graph? All right. In our syllabus, for feedback control stability, we only use route array or route stability criterion. For the route stability criterion, we need to have a transfer function in terms of polynomials. Therefore, uh, if you have some poles or zeros, so all you need to transfer. Okay. Apa yang kat atas tu in the denominator apa? Poles or zeros. Okay. The denominator you need to transfer any value of coefficient at the denominator. At the denominator, you need to estimate it such that you will have a polynomial, a straight polynomial equations. Right? There is a response, what we call it, frequency response, in order for us to analyze the stability. But in that case, we don't cover in our syllabus. Right? Frequency response require you to do the plotting. You need to use a lot of MATLAB script in order for you to plot it. But what's covered in our syllabus is just a route stability. So make sure that you transfer your transfer function, either that is from the servo or regulator problems. You have some coefficient at the top, in numerator, convert it. Okay, convert it. Oh, sorry, because the route stability, we just use the characteristic equation, so we don't care about whatever you have at the numerator. We just use the characteristic equation. But if you have a certain, for example, a time delay, then you need to convert it. For example, once you estimate your first your process from the process reaction curve, then you will obtain first order plus time delay. Then you need to estimate that time delay into the S domain, or into the tau. Sorry, convert the time delay into tau. Otherwise, you cannot use the tau. Oh, sorry, the theta in your characteristic equation. Of course, poles and zeros basically have effect and impact to the stability. Okay, depending on where it is located in the graph, in the imaginary graph. Okay, you will have an imaginary because some of these value of the poles and zero can be positive and negative. So you need to check the stability, the location of this value of poles and zeros, and from that you can identify whether it is negative, or is it stable or not. That is the general, but for us is stabilities depend on the what kind of range of our controller parameter that makes our closed loop system stable. Okay, but general stability, yes, that is the question. That is the how you determine the general stability of your process by looking at the location of your zeros and also poles locations. Right, but for our syllabus, just use the characteristic equation because we just analyze the route stability criterion. Okay, guys, if you have any question, just comment it. Just post a comment in the chat so that I can answer it or make clear or justify it. Let me check why that there is no tak ada komen yang masuk. Okay, tak apa. Oh, alright. Understood. Thanks, Prof. Alright. So, ada lagi soalan nak ditanya, especially for your test tomorrow night. Again, all of this depend on your understanding of the block diagram. That's why the block diagram is the first question that being asked in the second test. Usually, we'll ask you to draw a block diagram. Once you draw the block diagram, then you need to identify or put all those transfer functions related to your block diagram. All the blocks need to have a certain value of the transfer function, and after that, you convert or you derive the closed loop transfer function in terms of servo or regulator problems. And this simplified transfer function equation, you need to use to plot or sketch their dynamics response. If you're asked to sketch, make sure you know how to find the initial value and how to find the final value using initial value theorem and also the final value theorem. Okay, make sure that you're able to apply this initial and also the final value theorem. So you know the initial, what is the initial, you know what is the final, and in between you just look, okay, what type of order of your transfer function, either first order or second order or higher order. And from that, you just just sketch it. So it's not exactly how like you plot it, okay, but at least we know that, okay, first order, this is the behavior of the first order. The second order under them, this should be the behavior. Of course, it will be the same as first order. Over them and under them. Under them will be different. First, higher order or first order plus time delay will be different from first order. We have discussed this before. Okay. The first order plus time delay, or we call it process reaction curve, is basically different with the first order. There is a slightly curve in the beginning of the increment. Kalau first order, dia terus naik. If you apply the step change to your input, the first order dia terus naik. After you apply the step change, dia terus naik. But for the process reaction curve ataupun untuk first order plus time delay, there will be slightly delay and a curve response before it starts to increase. And that's how we differentiate between the first order and the first order plus time delay response. Guys, any other questions? Then you come to the stability, find the range, and after that, tuning. When you want to compare the performance of your tuning parameter, make sure that you compare it based on their performance, dynamic performance, not the tuning parameter values. Especially if you have a second order under them response. There is a lot of things that you need to compare. For example, if you're given two tuning parameters, the same process, but you're given the two tuning parameters, and the response behavior like under them, second order under them. So what you need to do is you sketch, or sometimes you give you the plot, the response plot. Make sure you identify it, you analyze it, or put a graph or a table, compare it in terms of time rise, in terms of settling time, in terms of offset. Oh, sorry, yeah, offset. Not offset because this is a will have an offset. Overshoot, decay ratio. Okay, rest time, overshoot, decay ratio, setting time. So at least these four you need to compare before you come up with the one solution, the best controller tuning. Okay. Izati again, initial value theorem, how to calculate, is basically reverse to the final value theorem. In the final value theorem, the time is, you calculate the time, or you analyze the response at the infinity, at the time equal to infinity. If you have a time at the infinity, therefore your S will be at 0. Initial value theorem, you define or you analyze the response at time 0, t equal to 0. Okay, check back your text. That's how you apply the initial value theorem and also the final value theorems. Final at the infinity, initial at the time equal to 0. Okay. Any questions, guys? Okay, we're waiting for another question. Yeah. Nur Fatiha, how to know the initial and final value theorem? All right. Again, okay, the difference between initial and final value theorem is where you want to analyze it. Initial at t equal to 0, final at t equal to infinity. All right. And for the initial and value, you should refer to the equation. You should refer to the models. Initial value, of course, there must be some model related to initial value theorem, and there is also a equation related to final value theorem. But the difference is, if you want to, okay, as I mentioned before, if you want to know your response, if you want to sketch your response, you need to know the initial and also the final value of your response. So where should be your start, your response start? So you should start initially at time equal to 0. Therefore, you need to use the initial value theorem. From that, it will give you your initial steady state value. And after you have a step change, then you will have a certain response and you will end up at a certain value. That's we call it final value, a final value. And this final value, you can identify it using final value theorem at time equal to infinity, because one is already settled to one steady state value, it will be remain the same unless there is some disturbance. Okay, that's why we evaluate it at the final value theorem, at the final value at the t equal to infinity, because we assume one is already settled, it will remain the same. It will remain steady state until there is a no there is a disturbance change, disturbance come to your process. All right, for sketching the behavior, what is the axis? Okay, it's depend on your control variable. The x will be the time. It's depend the unit. Make sure you use the right unit. The y is depend on your control variable. If it's a composition, so you just use the composition. Okay, between 0 and 1. If it is temperature, make sure you know it should be temperature. It depend on your control variable. For example, in our composition, sorry, composition control for a blending system. So is our control variable is basically a composition. Okay, our control variable should be a composition. So just the y-axis should be composition, and the the x-axis should be time. So that's why we you need to calculate the initial value at t equal to 0 and the final value at infinity. Okay. All right. Any other question, guys? We will have another 5 minutes before we end this online session, online discussion sessions. All right. So make sure that your all your tests basically cover these 5 things: the block diagram, the transfer functions, dynamic behavior, stability, and also tuning. Okay, all these 5, make sure that, but all these 5 basically come from the block diagram. Make sure that it is important for you to understand and master the block diagram. If you draw the block diagram, if you draw a wrong block diagram, if you label a wrong block diagram, then the rest will be affected, especially in your transfer function and also in your uh, dynamic behavior. That's why label is important, because you ask about the axis here. Exactly, you ask about the axis. So therefore, it's very important for you to label in your block diagram what is the unit of your control variables. Composition, for example. Therefore, your y-axis, your y-axis should be composition. Okay. Let's us look at this Menti. 34 of you respond to this survey. Okay. Okay, nothing changed there. Still remain the same. Block diagram, because block diagram is very important. And then transfer function, yeah. Stability. I think stability, if you're given the stability question, that's become a bonus for you, because yeah, we only use or analyze one single stability criteria here, which is route. Tuning, yes, because you will compare these two method of tuning, offline and online. So that's why for you, you think that this is a little bit difficult, because you need to compare between these two things. Okay, these two methods. All right, guys. Any other questions? Okay, if no more questions, so once this, because this will be recorded by YouTube, once this has been uploaded or processed by YouTube, then I will put this, I will edit it, and I will put it in your in this YouTube, and you can look at it, and yeah, you can learn from it. Yeah, Shamila, well, the table given for Ziegler, Shamila, this is an open book online. If you're not given you any table for this, you just Google it. Or you have your book. So prepare. You put all the how many books to, in front of you is okay. All right. So this is different with the online, and also because in online we assume that all the references are already with you. Or if you're not having the reference, you can basically uh, Google it if you have a time. But answering your question, no, we not provide any model, any equation related to either Ziegler-Nichols or Cohen-Kuhn, because we assume that you already know where and how to use it and where to find it if we are not uh, if you are not given these formula or models. All right, Shamila. All right, thank you. So if you still have, if you want to ask question, you can also make a comment here in this link. Then once this YouTube recording been processed by YouTube, then I will put that in a new link such that you can also look at this. Okay, but all the question here is basically have been highlighted here, so therefore you can able to refer it back. All right. So hopefully that this simple 1 hour, less than 1 hour online discussion will basically help you in understanding this feedback control system analysis, especially for the plot diagram, for the transfer function, and also the dynamic behavior, and the most important, these two: analysis, stability, and tuning. All right. So all the best for your test tomorrow night, and there will be some instruction, specific instruction that basically I will inform you tomorrow evening. Okay, such that it will make our organization of this test become more efficient compared to the previous one. All right. So, guys, thank you very much for watching and also for participating in these online discussions. So we see you at in the others online discussion soon. All right, thank you very much. Wabillahi taufiq wal hidayah. Assalamualaikum warahmatullahi wabarakatuh. Those who still don't subscribe this channel, please subscribe. Click the subscribe button so that you can have a lot of information, new information related to process control, related to EduTube, and also about the teaching and learning. All right, guys, thank you. Bye bye.